We're going to go today until we either finish the notes or we run out of time. So that's our goal. All right, we've already studied buffers. You guys kind of considered those. We saw that we weren't getting any fluctuation here for the most part with the pH because the buffer was kind of handling that. Your blood has a great amount of buffering capacity. That's why when you drink certain things or eat certain things, your body can handle it. Okay. As you get older and you are able or have the opportunity and you choose to, you can drink alcohol. Okay. And your body can buffer out that alcohol to a point. But then you get to the point where it overwhelms the system and people die from too much alcohol. That's why when you guys go to college, a lot of you will make bad choices because you're under 21 and you will binge drink. Okay. And you have to still be careful with that. But the problem is that the alcohol takes away some of those inhibitions and you continue to drink. So be very careful. Have someone with you if you make those bad choices to make sure that you are not going too far with it. Even after you're 21, you can still make those bad choices, and you have to be careful with that because your body only has a certain amount of a system to be able to deal with it. Okay. I know none of you have done that at this point because none of you are 21 yet. So yeah. Nope. Not my good AP Chem kids. All right. So, if an acid is introduced to a buffering system, that base in the buffer is going to attack the acid. Okay. So the base attacks the acid attacks the base. All right. So if we had a system here that had 2 moles of acetic acid, 2 moles of sodium acetate, and it's dissolved in water, that buffered system, since it's a weak acid conjugate base present, is able to handle the introduction of this strong base. Well, it can be a strong base or a weak base, actually. Okay. At any rate, you've got a 0.1 liter here, a 0.1 molar, okay? And you're going to do this in moles, okay? And we can actually determine if we know the Ka value or pKa value of acetic acid, then we can actually calculate pH. And that's what we looked at before, okay? And these become mole problems. So that's why you've got to, like, I always just take these. You'll see a lot of times in my notes that I'll have these like a little tent drawn between them. And then up here, I have a number. And that number usually is whatever the moles are. Okay. So I just go ahead, when I see something like this, I just go ahead and calculate that right into moles, which I think this would be 0.001. But I'd have to do the math. Oh, yeah, 0.01. Sorry. Guess I need to do the math. All right. Same idea applies here. If you are adding an acid in, that's going to attack the conjugate base. It's going to react with that and form new acid. And see, the beauty behind these buffer systems is if you add one thing in, it creates the other part of the buffer. If you add the other thing in, it's going to create the other part of the buffer. And as long as you're going back and forth, you're never going to exhaust that buffer. Just kind of cool if you think about it. All right. So here they want us to just create and look at what these conjugate acids or bases are. Remember, acid, there's always more H plus, and base, there's less H plus. Okay, so here, if we're going to add an H plus onto this, that's going to become H2PO. What's going to happen to my number here? Is it going to be -3 or -1? -1, right. We added an H plus. 1 plus 2 minus is going to give me a -1. All right, over here, we're going to take an H away, PO4. So what's going to happen to my number? It's going to be a -3 or 3 negative. All right, here we can't add another H in. It doesn't work. But we can take an H away, and if we do that, then we will just have H2O with no charge. All right. Fluorine, again, I can't take a negative away, but I can add a hydrogen. And if I add a plus, then that's going to make my negative go away. See if you can do the next one. Oh, shoot. Do okay on that? Did you get it right the first time as opposed to me writing in the wrong box? Good job. I fixed my boo-boo. All right. We have a buffer system here. We have H2S and we have NaHS. Remember that this is going to ionize. It's going to go as an ion because sodium's always soluble. And when we put that into water, we're going to have these two ions floating around. And this ion then is going to be your conjugate base for this guy. So they wanted us, we have a 3 mole of each. So I'm going to draw in 3 of these. So 1, 2, 3. I've got sodiums. I have 3 of those, and I'm not shading in my triangles. I'm going to be a rebel today. And then I'm going to have 3 of these. All right. If I introduce an acid into this, then the H plus from that acid is going to go with this, and it's going to turn it into a solid circle because it's going to make H2S. Okay. If I have a base introduced, then it's going to strip away one of the H's from here. This will become this then. And it's also going to form water, which they told us not to write on there. Okay, so let's look and see what that would look like in terms of equations here. Write an equation that would take place if a strong acid were added to the system. So if I add a strong acid in, that's going to introduce H plus ions. The H plus ions then will react with our conjugate base, which is HS minus. That is then going to form H2S plus water. All right. If we add OH minus into the system, OH minus is then going to go with our H2S. It's going to react by pulling one of those hydrogens away to make water. And remaining then is going to be an HS minus. Make sense? Everybody's good with that? I think after doing those posters, this kind of just it becomes a little bit more easily manageable. This used to be the point where we were hitting buffers at the beginning, and I'm trying to do this year to see if it'll help some now that I've made my peace with buffers. All right. I'm good with that? All right. Let's go back and do some Henderson-Hasselbalch equations. I always think of that David Hasselhoff. You know, David the Hoff. Yeah. That's what I always think about here. All right. This was the old way of doing it. We're not doing it that way anymore. And I think I pulled that off of your sheet even. So some of my answer keys still have that on there, but I'm working to revise them. So we are going to revisit this equation here. And you have stuff printed in your... Do you have stuff here in this blank? Okay. Okay. So you got that. All right. So this is your acetic acid. We have our pKa for that. Okay. They want us to calculate a pH of that buffer system. So pH equals your pKa, which was given in the problem. If they give you a Ka, you just take the negative log to get this value. Then we need to add our log in of our base on top and acid on bottom. Okay. So my base, and I want to do this as moles. Okay. They gave it to us as moles, so that works. But, all right. Log of 1 is what? 0. So our pH will end up equaling 4.76. Because this is 1. You should be able to do that in your head. All right. All right. All right. So we have pH and we have pKa that have the same, because the concentrations are equal. Yeah, we just did that. Okay. So we have 0.1 moles of NaOH are added. It's going to react with the acetic acid to form a conjugate base, as shown in this equation. So if we were to try to figure out, it looks like they want us to figure out the pH for this. Okay. We have our 4.76 because they're still using the same buffer, right? Yeah. And they want us to do log, and we're going to do base on top, which we had 2 moles of that. We had 2 moles of the acid. And we're adding 0.1 moles of NaOH. Is that going to take away from the acid or the base? Acid. So I'm going to do minus 0.01 and plus 0.01. So when I do that, do they have the words on here? They already have this solved, right? Okay. I end up with the same pH because this is such a minuscule amount that it really doesn't even end up affecting this value. Okay. But that's why these buffer systems work, because you can add that base in and it has virtually no effect on it at all, which is, I mean, if you think about like kind of the simplicity of it, but yet the fact that it works so well and it creates the other things so that when you add something else back in, it's like this give and take system. It's just, I don't know. Sometimes in science, some of the stuff is just like awe-inspiring to me. I'm nerding out now, guys. I apologize. All right, we've got the same system here. We're going to do our pH of this guy. We have 4.76 again, plus the log of our base, which we said was 2. Our acid was 2. And this time we're going to have acid added in. So which one is that going to attack? Is that going to attack the base or the acid? The base. So we're going to minus 0.01 plus 0.01. And guess what? The pH ends up being 4.76 again. Because again, this is such a minor change that you're not going to affect it that much. All right, next one. We have our pH here that we're going to calculate. weak acid HA. They gave us a Ka value here. So we need to figure out what the pKa is. So anytime we want to find out the P of something, what do? Negative log. So we're going to take the negative log of this value. When we do that, we get 4.82. All right, we got to figure out, they didn't give us volume here, but it doesn't matter because we're not taking anything or giving anything away. So we can keep these as molarities. Okay. And they said that the A minus concentration, which goes on top, is 972, and the H concentration is 0.137. So when I do this, I end up with 5.67. Does that make sense where I got the values from? Yep.
Where'd you get the 4.82?
I took the negative log of this. So anytime you want a P of anything, so pH, for example, you're going to take the negative log of the H. If I want the pKa, I'm going to take the negative log of the Ka. If I want the pKb, I'm going to take the negative log of the Kb. So the P of anything is the negative log of that thing. That makes sense? All right. Anything else that we need to talk about? No? Okay. All right. So they want us to calculate the Ka now. So we've got Ka that we're trying to deal with here, but they gave us the pH. So pH is here. So 4.219 equals Ka is what we're solving for, plus the log of, and they gave us moles this time. Remember, you can just use moles in here, and that works out just fine. You could go through and calculate, they've got it here. We could go through and recalculate the new molarity and all that crap, but it doesn't really matter because the moles work in here, okay? This value right here, is that going to go on the top or the bottom? The bottom, yep, because my acid goes on the bottom and the other one's going to go on top. Okay, then I'm going to find out this value, and what am I going to do with it? Find out all of this. What am I going to do? How do I get Ka by itself? Yep, I'm going to subtract it from this value. Because remember, whatever you do the opposite of it to get out of there. Okay, so this is added in. If I want to get rid of it, I'm going to subtract it from both sides. So when I do that, I end up with a Ka value that is 4.35 times 10 to the negative 5. What are my units?
Isn't it nothing?
No, yep, correct. We have no units. K values are unitless. So are pH values, by the way. H values, however, are not. If you take 10 to the negative this, then what do you got? What unit would you have? 10 to the negative 5.67 would give me what? This is pH. So 10 to the negative 5.67 will give me what? Huh? I don't want the value. I want the units. Yep.
The molarity of H plus.
Yes, molarity of H plus. Because remember, if you take the negative log of this, that's going to give you the pH. Okay, yeah.
So in the normal thing, it was like the pK plus the log of the base over acid. But do we take the negative log of our answer, or is it? Can we substitute PK and KA in the same thing?
So here we got an answer, right? So we got an answer. This ended up being our pKa. This is pKa. I should have pKa there. Bad Lippy. So this was 4.36. And then I just did 10 to the negative 4.36 to get this value here. Better? Does that make more sense? Derek, did I answer your question?
Yeah.
All right, good. Well, we are ready to move on to the last part of Unit 8. Are you excited? All right, you ready? You ready? You ready? All right, buffering capacity. How much can this take without getting overwhelmed? Okay, so buffer capacity is a term given to the amount of acid or base that can be added to a buffer system without the pH changing by more than a unit of 1. To increase the capacity of the buffer, you increase the conjugate acids and conjugate base pairs and keep the same ratios. Okay, this keeps the pH of the buffer system the same, but means that there's more stuff there to be able to neutralize those invaders. Okay, so here we have 2 buffer systems. And I think I cheated and gave you guys the info already on it, didn't I? I messed up. I should have made you do all this. All right. So here we have 0.1 molar acetic acid and sodium acetate. We have a 1 liter system. Okay. So if we have a 1 liter system, then that means that these are also our moles. Okay. So if we set this up with our equation, our pH is going to equal our pKa, and they told us our pKa here is 4.76 plus the log. We initially have this set up. They are both the same values. They are both 0.1 since we're dealing with a 1 liter system. Good? Everybody do that math with me so far? Yeah. I have an invader. I have an OH that's invading. What's that going to take away from? The acid. Is that the bottom number or the top number? Bottom. So I'm going to do minus 0.05. And up here, I'm going to do plus 0.05. I go through and I calculate my pH. They want us to calculate pH on this, right? Yeah. So that ends up being 5.24. Now you can see the way they did it, and you may want to write down the way I did it. I think the way I do it with the moles over here is much easier than having to recalculate volume over and over again. Or not volume, calculate volume and then get to a new molarity. Does that make sense? I think this is a much more simplified way of doing it, to be honest with you. And you don't have to bother with all those ice tables and everything else. I mean, look at how much space they took up versus how much space I took up. Look at how much time it took me to do this versus how much time it would take you to draw out that stupid table. Yes? What y'all need?
Where Miss Negus sent us.
Mm-hmm.
For the etching.
Okay.
About the etching.
So go back there in that back room and find Nicholas Albee. You know who he is? He knows how to deal with it. I gave him the recipe.
Okay, thank you so much.
And if he can't do it, go to the next room over. Mr. Schramm is the one that actually made it for y'all. All right. So here we have a system. We've got our pH equals 4.76 plus the log. We've got the same buffer present, 0.1 and 0.1. This time, though, we are adding, oh, wait a minute. Do they just keep, no. Do they add another 0.05? What are they doing here? What am I doing wrong here, y'all? This we added in acid. Are we adding in different amounts or something? What's the difference between these two problems? Help me out here, you guys.
Buffer A is 0.1 molarity and buffer B is 1.
Oh, that's it. Okay. I was like, I for the life of me, I could not figure out what I was doing wrong there, you guys. Okay, thank you very much. All right, here we go. So this is 1, right? Yeah. I need to read the problems. It's Monday morning. What do we say, Haley?
Huh?
It's Monday morning. What do you always say? It's a Monday. Happy Monday, Lippy.
Happy Monday, Lippy.
Happy Monday.
It is a Monday.
All right. So let's try this. We've got ones here now. We're still going to, we're adding OH in. We're adding the same amount of OH in. We're going to see how this affects the pH. So here the pH is going to get affected. It's only going to be we're going to end up with 4.82 here. No, 4.80. Definitely a Monday. All right, there we go. So why are these not continuing to show up? So you can see here that if we have more buffer available, we have more conjugate acid and base, that keeps the pH from swinging even more dramatically. Does that make sense? So the more you have of the conjugate acid and base, the less the pH is going to swing back and forth when you're introducing these acids and bases into your system. Okay? So the buffer with the higher concentration is going to resist the pH more than the lower one. All right, let's try this one, see if I can get this one right. So we have 0.1 molar, 0.1 molar. We're adding this to the buffer system. Will it react with the acetic acid and the amount of the acetate will increase? It's going to change the pH. So they want us to calculate the pH here, right? Okay. So our original system up here, if we had that, we had 0.1 and 1. Okay, so we've got our pH is going to equal 4.76 plus the log. We've got our acid on the bottom, which is 0.1, and we've got our conjugate base on the top, which is 1. So we're going to figure out our pH here. When we do that, our pH is going to equal 5.76. Now, they are going to introduce OH, 0.05 OH into here. So the pH will equal 4.76 plus the log of 1 and 0.1. Now we got to figure out what's going to happen here. We're adding OH in, so what's that going to take away from? It's going to take away from the acid, so minus 0.05. And we're going to add 0.05 here. And when we do that, our pH is going to equal 6.08. So what's that a change in? We went from here to here. How much is that? It's written on your paper, you guys. You got the cheater copy. Yeah, 0.32 units. And we don't have units on pH. So, all right, now we're adding acid in. So we've got the same buffer system. So our pH is going to equal 4.76 plus the log of 1 and 0.1. All right, so this is going to take away from which value, the top or the bottom? The top. It's going to take away from the base. If you introduce an acid, it's going to attack the base. And we're going to, now, before we do this math, let's think about this, okay? If I have a buffer system where I have more base there, is that going to be able to handle more of the change of acid or more of the change of base introduction? This is a bigger number, so what's it going to be able to handle more of? An introduction of acid. So here we would expect our pH to not go down quite as dramatically, right? So pH equals 5.56. Okay. We said originally that our pH was 5.76. So you can see that that changed by our delta pH here is, you can do that in your head? Okay, 0.2. So you can see that it didn't change quite as much with the introduction of that acid. Make sense? All right. I do. All right, we want to calculate the pH for the buffer. So we have our pH here is going to equal our pKa, but they gave us a Ka. So our pKa, we're going to take the negative log of this value, and we are going to get our pKa value of 4.19. All right, let's see here. We have to, I want to get these into moles. I could, yeah, you want to get these into moles, okay? You could go back and recalculate your new molarity, but again, it's kind of a waste of time in my opinion. All right, so this is 0.1, and this is 0.2. Yep. So I'm going to do my acid on the bottom. I'm going to do my base on the top. And I'm going to find that my pH then equals 4.49. All right. Will this handle more acid or more base addition?
Acid.
Right. It's going to handle more acid because we've got more of the conjugate base here. So it's going to change more if we add more base in. Now, did they ask us to explain this problem?
No.
They just asked for an answer. On your AP exam, if they just ask you to answer the question, just answer the question. Don't go on and elaborate. Because if you elaborate wrong, even if you circled the right answer here, they will mark it wrong. Okay? Answer the question and move on. Okay? You're not trying to prove how smart you are. You're taking AP Chem. That's already been confirmed. You've made it to second semester. You are good. You're taking the exam. Okay? If you're taking the exam, you're smart. You're smart anyway. Love you. Lexi, love you. Smart anyway. But, I mean, y'all, you're smart. I mean, you look at some of your compatriots here at school, you're smart.
Oh, I know.
All right. Here we go.
I think we all in this room have common sense manuals.
Yeah. All right, here we go. You ready? You ready? You ready? So, buffer X is created here. They want to know the pH. So what I did on my answer keys is I just did pH here, and then I showed you down here how to do the problem. Okay? Going too far. Make this a little bigger. All right, so here we've got our pH is going to equal our pKa, which they gave us right here, plus the log, and we're going to have, and they've already got it in moles for us, which is really nice. So this is my bottom number, and this is my top number. Okay, when I do that calculation, the pH for this guy equals 2.9. All right, do the next one. 0.2 plus the log of, this time it's flipped around. I've got 0.5 on the bottom and I've got 1 on top. So that ends up equaling 3.5. And the next one is pH equals 3.2 plus the log of HA is 2 and the base is 4. This ratio is the same as this ratio. Why would it be better to have this ratio though? Right, there's a lot more buffering capacity here. It can withstand much more addition of stuff in. Even though the ratio is the same, you're starting out of the same pH, this is still going to be able to handle more stuff getting added to it. So again, they just asked us for the answer. We're going to say Z. They didn't ask for an explanation. They don't ask for an explanation. Don't you go and explain stuff. Okay? Because again, you get that explanation wrong, it's all wrong. All right. Guess where you're at, guys? You're at the progress check, Unit 8. We have 1 unit left, and we're getting close. I have your schedule actually for Unit 9 created here, if it'll let me get to it.